In this video, we're going to be talking about the calculus involved with parametric equations. It's not a terribly long section, and it's actually kind of fun, so I hope you'll enjoy learning about how to find the derivative and the second derivative with parametric equations. Let's get started while I share my screen with you. There we go. All right, so now what we want to talk about is how to do calculus with parametric equations. Remember, we talked about parametric equations being a set of equations, a pair of equations, x of t and y of t. That's in 2 dimensions. If we had 3 dimensions, we'd have x of t, y of t, z of t, where t is actually the independent variable, and it's called a parameter. So x depends on t, y depends on t, and if we have 3 dimensions, z depends on t. Now we're going to stick in the plane curve today, and remember the plane curve is another way of describing 2-dimensional space, so the flat xy plane. So what we want to talk about is how to do calculus with these parametric equations. Now remember, we said parametrics are good for situations where something in location depends on time. So it not only tells us where the object is, but when the object gets there and the direction or orientation of the path it follows as it moves along a curve. It's great for curves that are not functions, and also great for curves where it cannot be explicitly solved for y. So it may have both y and x in the equation, but you can't get the y's together on one side and solve for them. So parametric equations are really good for those kinds of things. When we're looking at calculus, we want to start, of course, with the derivative. So when we're looking at derivatives of parametric equations, we need to think about what is the derivative really. So when we're talking about the derivative, remember that we're talking about the change in vertical position with respect to the change in horizontal position. In other words, I don't care what coordinate system you're using, and the derivative is always, and I don't get to say always very often, always dy dx. So when we're looking at this, you need to remember that the derivative is always going to be dy dx, no matter what coordinate system you're using. And we are going to learn another coordinate system in the next few days. That's going to be the polar coordinate system. Now, there are many, many coordinate systems. I know it seems like there's only the rectangular coordinate system where you've got the x-axis and the y-axis, and it looks like a rectangular grid. That is not the only, I mean, there are books that are 3 inches thick of different coordinate systems. So there are all different kinds of ways to graph things. But no matter what kind of graph you're using, what coordinate system, the derivative is always dy dx. Now that's going to be a problem for us because dy dx doesn't have a t in it anywhere, and t is actually our independent variable now. So we need to come up with a way of expressing dy dx that relates it to x as a function of t and y as a function of t. In order to do that, we're going to have to use a complex fraction. There's no way around it. Now, for those of you who are wondering, what's a complex fraction? This is a complex fraction. It's basically a fraction within a fraction. So when you're looking at something like this, you have the numerator of the numerator, denominator of the numerator, numerator of the denominator, denominator of the denominator, all right? Or top of the top, bottom of the top, top of the bottom, bottom of the bottom. Now, I always like to think of it this way. The top of the top and the bottom of the bottom are on top, and anything with a top-bottom mix is in the bottom. And that actually is the rule. So in order to simplify the complex fraction, you can take the denominator fraction and multiply by the reciprocal, which will give you a over b times d over c. So that this actually came out to be, if you rewrote it in a different way, this comes out to be a times d divided by b times c. And like I said, the top of the top and the bottom of the bottom are both on top when you simplify. And anything that's sandwiched in between in the middle goes to the denominator. So I always like to tell my students the bottom of the bottom is the top. It's just, it rolls off the tongue and it's easy to remember. And so students have an easier time simplifying those complex fractions. Now, do be careful when you have something that looks instead like A over B over C. You have to know which one is the primary division bar. Is this A over B in the numerator divided by C in the denominator, or A in the numerator divided by B over C in the denominator? Because it will give you a different result. So what I tell my students to do is to make the primary division bar longer. In this case, I made the one between B and C longer. So the correct way to interpret this one is A over B over C over 1. So this one, of course, turns out to be A over BC. So be sure that you understand the difference between that and this. When you have this one, this needs to be interpreted as A divided by 1 over B over C. And this one is going to turn out to be AC divided by B. So you need to make sure you know which one is the primary division bar. Now, where does this complex fraction come into play when we're talking about derivatives in parametric equations? We're going to start with a plane curve. And by plane curve, again, we do mean something in the two-dimensional space, the XY plane. And it's defined by a pair of parametric equations, x equal x of t and y equal y of t. And we're going to assume that the first derivative of x of t and the first derivative of y of t exist. Now, when I say the derivative, I mean the derivative with respect to t, because t is the independent variable. So dx dt and dy dt exist. And I'm going to assume that dx dt is not 0, and you'll see why in just a second. Then the derivative dy dx is given by an abusive notation. So what we're going to do is we're going to take this dy dx, we're going to take the derivative of the numerator, which was the y, with respect to t, and then we're going to take the derivative of the denominator, the x, with respect to t as well. So I have dy dt divided by dx dt. Now the question is, okay, this is really a derivative operation divided by a derivative operation. Okay, there is one fraction, which is the derivative divided by the derivative, but there really isn't another division in here. But we can treat it like their division. I know that's crazy. It doesn't make any sense at all, but it works. That's the genius of Leibniz's notation, and because it works, we do it. So it's an abuse of notation. So what I'm going to do is I'm going to split this up as I talked about doing over here, and I'm going to take the denominator derivative, and I'm going to divide by it by turning it upside down, taking the reciprocal, and multiplying by it. And this gives me dy dt times dt dx. Now, total abuse of notation. This mathematically makes no sense at all, and yet it works, and so we do it. I'm going to cancel the dt differentials, which gets me right back around here to dy dx. So in fact, we see that it is equivalent to dy dx, taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. This is why we don't want the derivative of x with respect to t to be 0, because, well, thou shalt not divide by 0, cardinal rule in mathematics. So this basically gives us our formula for the derivative with parametric equations. To find dy dx, which is always the first derivative, no matter what coordinate system you're in, you find the derivative of y with respect to the independent variable and the derivative of x with respect to the independent variable, and you divide them together. And this, of course, supposes that the denominator derivative is not 0. Now, they both have to exist, and the denominator can't be 0, but in our cases, that will primarily apply. Okay, in physics, if you had something like this, how might you interpret this derivative formula? Well, if you think about it, dy dt, y is vertical position. So the change in vertical position with respect to time well, that sounds like velocity, right? So this is basically the vertical velocity dy dt. And dx dt, well, x is the horizontal position. So the change in horizontal position with respect to time, that also sounds like velocity. So basically the derivative here, the slope of the tangent line at a given point on the curve, is equal to the vertical velocity divided by the horizontal velocity. That's just one way to interpret it. Now we want to take a look here at example 1. We want to calculate the derivative dy dx for a plane curve defined here for t between -2 and 3, and we want to locate any critical points on the graph. Now remember, how do we find critical points? Critical points are places where the first derivative either does not exist or the first derivative is equal to 0, okay? Remember, these are possible locations for extrema, relative maxima, relative minima, absolute maxima, absolute minima. So we're going to start off here, and we're going to write down our formula. Dy dx is equal to dy dt divided by dx dt. And again, make sure when you're doing a complex fraction that you make the primary division bar longer than the other two. So now we need to find dy dt. Well, y is 2t cubed minus 6t. So we just take the derivative of it. I know you think, well, that's too easy. Well, this is not as hard as series. So hopefully you'll enjoy this section. So we get 6t squared minus 6 divided by, and then we want to do dx dt. Well, x of t is t squared minus 4t. So we just take the first derivative with respect to t, and we get 2t minus 4. And then we want to clean this up a little bit. So I can take a 6 out of the numerator, and I can take a 2 out of the denominator, and I can reduce the 6 over 2 to give me 3. So I have that dy dx, the derivative, the slope of the tangent line at any point on the curve, is 3 times t squared minus 1 divided by t minus 2, right? So when we're looking at this, this is our formula, if you will, for finding the derivative at any point. So if I wanted to know on this curve, what's the slope of the tangent line when t is 1? Well, let's not do 1. let's do 0. When t is 0, since 0 is certainly in my range of values, -2 to 3, then I would plug it in here. So I would get -1 times 3 is -3 divided by -2, so I get 3/2. So at the point on the curve where t equals 0, the slope of the tangent line is 3/2. Now, of course, t doesn't show up on the graph. I would have to know what the coordinates are, and to find the coordinates, I would plug in 0 into x of t and y of t. And that would give me 0 here and 0 here. So it's at the origin. So the slope of the tangent line to the curve at the origin is 3/2. Now, why did I say let's not do 1? Okay, well, remember I said after you located the derivative formula, we want you to find the critical points on the graph. Well, it turns out that 1 is one of the critical points. So remember, there are two types of critical points. When you're looking at critical points, we need to find one of the following. 1, dy dx equals 0, or 2, dy dx does not exist, but y does. The function does. Now, I always write out this second one in longer format because it's not enough that the derivative not exist. The function itself does have to exist. In other words, that point has to be on the curve. Can't be a hole in the graph or anything like that. It has to be a point on the curve, but the derivative doesn't exist at that point. Now, typically that will correspond to something like a cusp or a corner, maybe a vertical tangent line, something like that. The curve exists, but the derivative does not. So we need to look for one of these two. Just looking at the formula, The first type is going to happen whenever the numerator is 0, and that's going to be when t squared minus 1 equals 0, and that's where I get my 1 and negative 1. All right, so we have plus or minus 1 there. Now, what about the second one? dy dx does not exist, but the function does. Well, first off, it definitely does not exist when t equals 2, but then I've got to make sure that t equal 2 is actually a point on the graph. So my candidate here is going to be t equal 2, but I have to make sure that I can actually use 2 in the function. 2 is in my range right here, and there's certainly nothing to stop me from plugging in t equal 2 into x of t and y of t. So it is a point on the graph, but it is a point at which the derivative does not exist, right? So we found over here that when t equals 0, dy dx equals 3/2. We're going to kind of take note of some of these places that we found right here, all right? And then we could also look at t equal to 1 and t equal to negative 1, and we could see what the values for x and y are, and we could look at t equal 2 and see what those values are as well. Now, here's a graph that you can see right here, and let me come up here and copy off my equation. And I want to add this down here somewhere. This might be a good place to put it in, okay? All right, so when I'm looking at the graph, this is the actual curve, and this goes between -2 and 3 for t values. So it actually goes up almost to about 35, something like that. I can't remember what the exact point is, but you could find it by taking either -2 or 3. I believe it's actually at 3 and plugging it in. So I've graphed it right here, and if we want to see how it's going to plot, then you would hit the play, and I have it pulled all the way back to -2, which is here, so it's going to curve and follow in this path. So our orientation for the curve, of course, is going this direction right here, and it's coming up here, and then it stops right there, right? So that's where it ends, right? So that corresponds to t equal to 3. Now, looking at the curve, we can see that we do have a relative max and we do have a relative min. We don't know which of the values it's at. We have 3 different possible critical points. So we've got t equal 1, t equal -1, and t equal 2. They are critical points, but are they relative extrema? Hard to say. So then you could do the first derivative test, or you could do the second derivative test. We haven't talked about the second derivative, so you can't do that yet, but you will be able to by the end of this video to determine whether it's a relative max or a relative min. In this particular case, I believe if we plug in, I'm not sure, let's test and see. So when t equals 1, what am I going to get for x? That would be 1 minus 4, which would be -3. And when t is 1, y becomes 2 minus 6, which is -4. So the critical point at 1 corresponds to this relative minimum that you see right here, right? What about t equal to -1? When we look at t equal to -1, this is still going to be 1, but this is going to become a +4. So that becomes a 5. And then the y value becomes, well, let's see, -1. So this becomes -2. This becomes +6. So that becomes a 4. And we see that we have the other relative extrema, which is the relative maximum here at 5, 4. So what about this last one that we have? Is it a relative extrema? I mean, it certainly doesn't look like there's another one. So let's go ahead and plug in that last one and see what we get. When t equal 2, I would get 4 minus 8, which would give me -4. And here, if I plug in 2, I get 8 times 2 is 16. 2 times 6 is 12. So 18 minus, did I say 18? 16. 16 minus 12 is 4. So it says there's something going on there at negative 4, 4. So if we look at the graph right here, what do you suppose is happening at negative 4, 4? So somewhere in here, it may be that we have a vertical tangent line, all right? So again, that would be correspond to a place where the first derivative doesn't exist, but the curve does exist, all right? So we have our different points on the graph. We've related the derivative that we found, the derivative formula, to different places on the graph. Note that we can also look where t is equal to 0. We said that corresponds to the origin. And when we look at our curve right here at the origin, what that's saying is the slope of the line as you're coming through the origin is 3/2, slope of the tangent line. So if I draw the tangent line in blue here, like that, the slope of that line is 3/2. So this is basically how you find the slope of the tangent line on a parametric curve. Now, if you want to find the slope of the tangent line at a particular point, for example, we just did that, we found the slope of the tangent line at the origin was 3/2, then we can use the tangent line equation in point slope form. So that's y minus y1 equal m times x minus x1. So for example, on the one we just did, we found the slope to be 3/2, erasing as I write, at the origin, which means the equation of the tangent line is going to be y equal 3/2 x, right? And that gives us the equation of the tangent line at that particular point. So it gives you the equation of that blue line that I drew. Now we can do that at any particular point that we want to do. And remember that the slope is just the first derivative evaluated at that particular point. So you plug in the values at the particular point. So let's take a look at another example. This is example number 2. And we want to find the equation of the tangent line to the parametric curve at the given point. So the point is 0, 5. Our parameter goes from 0 to 2 pi. And the equations for it are x equals 2 cosine t and y equals 5 sine of t. So to find the equation of the tangent line, we need a point, which we have, and we need the slope, which we don't have. So we need the slope of the tangent line, which is the derivative. So first we're going to find the derivative, dy dx, by evaluating dy dt and dividing that by dx dt. Now, dy dt, if I take the derivative of this, I get 5 cosine of t. And dx dt, if I take the derivative of 2 cosine of t, I get negative 2 sine of t. Now, this gives me basically negative 5/2 cotangent of t, but I don't think too well in terms of cotangent. So I'm going to stick here at just leaving it as negative 5/2 cosine of t over sine of t. Now, I specifically, this is a formula for the slope of the tangent line anywhere, but I specifically want to know what it is at 0, 5. So now I'm going to evaluate the derivative, dy dx, at the point 0, 5. Now, I have a problem. 0, 5 are x and y coordinates, and these are t values. So what am I going to do? Well, I need to know what t value causes this to be 0, 5. So I need to come down here and do a little bit of work. So when is x, which is 2 cosine of t, equal to 0? All right. Well, the only way that's going to be 0 is if the cosine is 0. Now, cosine is 0 at multiples of pi over 2 and 3 pi over 2. So we can write down pi over 2 or 3 pi over 2. Right? And multiples of those. But the problem is, I don't know which one it is. It could be pi over 2, it could be 3 pi over 2, and that's certainly going to lead to a different value of the derivative. But I also have a y coordinate, and the y coordinate is 5, and that's going to let me pin down which of the first two options it's going to be. So I'm going to take this equation, and I'm going to say y equal to 5 sine of t is equal to 5 when? Well, if it's equal to 5, then I can divide by 5, and that gives me that sine of t is equal to a positive 1. Now, the only time sine comes out to be a positive 1 is at multiples of pi over 2. Now, again, our t range is going between 0 and 2 pi, which means we only have pi over 2. So t must be pi over t. Right? Now that I know that t has to be pi over 2 to produce this ordered pair for the point, then I can take that value and plug it into the formula for the derivative. So this is going to be 5, the cosine of pi over 2 over negative 2, the sine of pi over 2. Now, the cosine of pi over 2 we know is 0, but again, the denominator can't be. So the denominator is going to be a negative 2. So this gives me, of course, 0. Now, what does that mean? It means it's a horizontal tangent line. So I've got some kind of relative extrema there. Okay, let's go ahead and take a look. Now, we want to write down the equation. So we're going to have y minus 5 equals 0 times x minus 0. And this gives rise to the equation y equal 5. Right? That's the equation of the tangent line at that particular point, 0, 5. It's a horizontal line, and you'll see it here in the picture. And there's a link down here if you want to play around with the parametric curve. And I went ahead and graphed the tangent line in a dashed red line that you see here, intersecting the curve at the point 0, 5. Remember, the tangent line touches the curve at that one point. And the slope of it is, of course, 0 because it's horizontal. All right. And that particular parametric equation produced an ellipse. Okay. Now, notice also, this is something kind of interesting to notice. The first one is 2 cosine of t. The second one was 5 sine of t. Notice that the 2 cosine of t produces an ellipse with a minor axis length of 2, right? So going all the way across, it would be 4, but from the center to the edge is 2, which corresponds to the 2 on the x equation. The 5 on the y equation goes in the vertical direction, and you can see that from the center to the edge along the major axis, it's a length of 5 from the center. Okay, the next thing we want to look at is example number 3. In example 3, we're looking at the same parametric equation we were before, but we're looking at a different point. So we're looking at the point square root of 2, negative 5 square root of 2 over 2, or you could write it as negative 5 over the square root of 2, since the square root of 2 over 2 is 1 over the square root of 2. So you can write it either way. Now, we've already done the equation of the tangent line. What we need to do is evaluate it at a particular point. So let's go to the work that we did previously. This is exactly the same equation. And we'll take this, well, not that. Let's see if that gets me everything I want. I think it does. So I'm going to take that value right there, and I'm going to paste it down here. All right. So this is the derivative formula that we found in example 2 for the parametric equation x of t equal 2 cosine of t, y of t equal 5 sine of t, which we know presents as a vertically oriented ellipse centered at the origin. Now, we didn't talk about the orientation of it last time. We'll look at the orientation of it this time and see which direction it's traveling. But this point right here is on the curve. And so we want to know what's the slope of the tangent line at that particular point. So you have to be given the point at which to evaluate it. So in this particular case, we need to change this information down here to being at this particular point. So we're not looking at 0, 5 anymore. What we're looking at now we don't know what it's going to come out to be, is the square root of 2, and I'm just going to write -5 over the square root of 2 to save a little space. All right, so that's our ordered pair. We don't know what t value gives us that particular point. So we need to find the t value by finding when x comes out to be square root of 2 and when y comes out to be -5 divided by the square root of 2. So let's come down below and let's work on that first. So we have x equal to cosine of t, and we want to know when is this going to be equal to the square root of 2. So we divide by 2 in order to isolate the cosine. So we get cosine of t is equal to square root of 2 over 2. Now you should have memorized in trigonometry the basic 6 angles, all right? Or basic 5, 6. Well, let's count them. I think there's 5. 0, pi over 6, pi over 4, pi over 3, and pi over 2. And then you can take those values and use the quadrant that it's in to adjust the positive and negative values. So you need to memorize those 5. When you get a value of square root of 2 over 2, it's always the pi over 4 radian angle. So this is 45 degrees. So I'm looking at this and I know that this is cosine and this is a positive value. So first I think, what quadrants is cosine positive in? I say cosine, you think x. Well, x is positive in quadrants 1 and 4. So I need something that has pi over 4 as the reference angle, but it has to be in quadrant 1 or in quadrant 4. So it's going to be pi over 4 and negative pi over 4. Now the problem is negative pi over 4 does not fit in my range between 0 and 2 pi. So what is coterminal to that but does fit in my range? Well, that would be 7 pi over 4. So coming around this way, we have 7 pi divided by 4. So my possibilities here are t equal pi over 4 in Q1 or t equals 7 pi over 4 in quadrant 4. And I don't know which one it is. I'm going to use the y value in order to pin down which of those two it's going to be. So now I'm going to start with the y equation, which is y equals 5 sine of t. And this time I want to use this value right here. And again, you can write it as -5 over the square root of 2, which simplifies it a little bit. So I have -5, and you can write it either way, equal to 5 sine of t. Now, the first thing I'm going to do is isolate the trig function. So I divide by 5, and I end up with sine of t equal to negative square root of 2 over 2. Again, square root of 2 over 2 is going to be a pi over 4 angle. But then I think, where is sine negative? Sine, I say sine, you think y. So y is negative in quadrants 3 and 4. So in quadrant 3 and 4, we need something that has a reference angle of pi over 4 here and something with a reference angle of pi over 4 there. So when I look at this, again, it's got to be between 0 and 2 pi. So coming around from the positive x-axis, this is 4 pi over 4. So 5 pi over 4 is one possibility. T equals 5 pi over 4, and that would be in quadrant 3. Or t is equal to 7 pi over 4 in quadrant 4. And then I look for the two and see what they have in common. Well, the only one they have in common, of course, is 7 pi over 4. So since they have 7 pi over 4 in common, then I know that that particular value that I need to evaluate it at is 7 pi over 4. So then I'm going to come back up here to where I have my derivative formula, and I'm going to plug in the value of 7 pi divided by 4 over 7 pi divided by 4. And it looks like I probably need some more space here. So let's see if I can move some of this down a little bit. And when I'm looking right here, the cosine of 7 pi over 4, well, I know what that comes out to be. It's telling me right here that it's the square root of 2 over 2. So when I write this down, this becomes 5 times the square root of 2 over 2, or you can write it as 1 over the square root of 2, whichever one you prefer, I use both. And then in the denominator, the sign of 7 pi over 4 is a negative square root of 2 over 2. But we also have this negative here, so we have a double negative. The double negative is going to make it positive. So this gives me 5 square roots of 2 over 2 over, and then these 2's are going to cancel. So this becomes over the square root of 2. Now again, note the importance of making the primary division bar longer. This is the primary division bar. If I want to make it look fully complex, which actually simplifies and makes it more clear what to do, I would put this over 1. Then the extremes of the complex equation, the top of the top and the bottom of the bottom, end up in the numerator. So this is going to turn out to be 5 square roots of 2. And then in the denominator, it's the things that are sandwiched in between, which is going to be 2 square roots of 2. And the square roots of 2 cancel, and I get 5 halves. That's the slope of the tangent line at this ordered pair on the curve, which is the ellipse, graphed by this parametric equation from 0 to 2 pi. Now let's write the equation of the tangent line, because that was our job. So we're going to write down y minus, and then the y coordinate was negative 5 square root of 2 over 2. Notice that's a different negative, equal. Our slope was 5 halves. And our x coordinate was square root of 2. Now let's do some algebra and simplify that. You never want to leave it like that if you could simplify it and make it more clear. So we're going to go ahead and multiply it out and move this over to the other side. A double negative is going to become plus. So when I subtract it, it's going to be negative. So this is going to give me y equal 5 halves x minus 5 square roots of 2 over 2 minus 5 square roots of 2 over 2. All right. Well, I've got 2 sets of negative 5 square roots of 2 over 2, which would be 2 of them. So this is going to give me y equal 5 halves x minus 5 square roots of 2. Because if I have 2 times 5 square roots of 2 over 2, the 2's cancel and I get 5 square roots of 2. So this is the simplified form of that equation that we see right here. This is the tangent equation in explicit form, meaning solve for y on one side by itself and nothing but the independent variable on the other side. Now let's go ahead and take a look here. We're going to take a look at the graph again. So here's our graph. And here's the point at which it's intersecting. Now, Desmos, unfortunately, will not give the exact values when you label it. It always goes to approximations, but you can see that this is exactly that ordered pair graphed here. And I've produced the parametric equations. We're going to actually click on this one so we can see the orientation. And here's the equation of the tangent line that we found. And we can see it's a dashed line. It is intersecting that point, and it's coming through exactly. Let's take a look at this graph now so that we can see what the orientation of it is. Give it a moment to open. All right. So this is the point right here, 5.49 blah, blah, blah. What is that in radians? Well, 5.4977 blah, blah, blah is 7 pi over 4. That's the angle at which the t value produces this ordered pair, right? So this is at 7 pi over 4 right down here for t, not 7 pi over 4 on the graph, obviously not, that would be here, right, at a 45-degree angle. T is 7 pi over 4, and t doesn't graph on here at all, so be sure you understand that. Now we're going to pull it all the way back to the beginning so that we can watch it trace. I made it an empty circle, and let's actually make it a little larger. I made it 14, which is pretty big, but let's make it even bigger, all right? And now we're going to play it and see which direction it traces in. So it's clearly going in a counterclockwise fashion. Uh-oh, what did I forget to change? I didn't change my link down here to only tracing forward one time. So let's pull it back again and trace it so we can be sure we have the orientation correct. So going around counterclockwise one time. Now, sometimes depending on the range of t, it may actually trace it twice, could even trace it forwards and backwards. So you've got to be careful that you know what the orientation is. So when we're looking at this one, it's going to start and stop right here on the x-axis at 2, 0, and then it traces the orientation in this direction, comes around all the way like this, and then it stops again at there, and it only traces it one time, all right? Let's now work example 4, which is finding the derivative again. So this time we're not asked to find the tangent line equation because we're not given a particular point. We're just looking for the derivative formula. So again, dy dx is dy dt over dx dt. So we're going to take that equation, dy dx equal to dy dt divided by dx dt. Always make the primary division longer. So the derivative of y, now we're going to have to invoke chain rule because we've got cosine of t quantity squared. So the 2 is going to come to the front, leave the cosine alone, reduce the power by 1, then take the derivative of the inside. Derivative of cosine is going to give us negative sine. So this is going to give us 2 times 3 cosine to the first power of t times the derivative of cosine is negative sine of t. That gives us our numerator. And now we're going to do the same thing on the denominator. The value of x of t is 2 sine squared of t. So applying the chain rule, we get 2 times 2 sine of t times the derivative of sine of t, which is cosine of t. Now I'm going to have a negative on top and a positive on bottom. I've got a 2 and a 2. Well, I've got 2 2's in the denominator, but only 1 on top. So one of these cancels one of those. And I'm going to have a negative 3 on top. And I'm going to have 2 in the denominator. And what else do I have? Well, I've got a cosine of t on top and on bottom. So those are going to cancel. So they disappear and go away. And then I've got a sine of t in the denominator and a sine of t in the numerator. Well, they cancel and go away. And that seems to indicate that my slope actually doesn't depend on t. Whoa, okay. So it doesn't depend on t at all. It's always a constant. Well, if it's always a constant, what graph has a constant slope? Yes, a line. So this must be producing a curve which corresponds to a slanted line with slope of negative 3/2. All right, so we're going to actually look at this particular graph, which is right here. It starts and begins at 0, 3, and this is going to trace it from 0 to 2 pi. Now, I want to look at this one in particular out here on the internet, because this one does something that we've not seen before, either in the last section or this section. So I kind of want to point out that this can happen, and you've got to be aware of it. So here's our parametric equation listed in the ordered pair, t going between 0 and 2 pi. I copied that and changed the variable to a, created a slider bar. A is going from 0 to 2 pi as well. I pulled the slider bar all the way back to the beginning, to the left. I've changed it to tracing only once. I think that's once. I can't read it quite. And then I'm going to play it one time. All right. So let's play. We can see that it's starting up here at 0, 3. And we're going to trace, it goes down and back up, whoa, and down and back up again. So in other words, it actually traces the curve twice, down and back up, that's once, and then down and back up, that's twice. Now, it's going to be really hard to show that orientation. You almost have to describe it in words. You would say it starts at 0, 3 and moves down to 2, 0, then back up to 0, 3. Then it traces that same path one more time, ending at 0, 3. Okay? All right. Let's now talk briefly about how you get the special tangent lines. That would be the horizontal tangent line, which we have seen today, and the vertical tangent line for parametric equations. Now, when we're looking at these, We know that a horizontal tangent line will only occur wherever the derivative is 0. Now, when do you get a derivative equal to 0? When you have a complex fraction, which is what the derivative is with parametrics, the only way to get 0 is for the numerator to be 0 and the denominator not to be 0. That means dy dt, the vertical change, has to be 0, but the horizontal change cannot be 0. So that happens when dy dt is 0, but dx dt is not 0. All right, what about a vertical tangent line for a parametric equation? Well, vertical tangent lines have undefined slope, and that's because the numerator is not 0, but the denominator is. So in that case, the numerator, dy dt, the vertical change, cannot be 0. Vertical change with respect to time or whatever t represents. But the horizontal change must be 0. All right, so this is a different situation. So you can see that we can get those two special cases by analyzing the formula for the derivative. The next thing we want to talk about is the second derivative of a parametric equation. Now, remember that finding the second derivative tells us about concavity. So it tells us whether the curvature of the curve is cupped up like a cup or down like a frown, right? So concave up, concave down. That's basically what we have, those two shapes right there. So when we're looking at these, we're looking for that particular thing, concave up or concave down. So what we're going to do here is we're going to have to find the second derivative by applying the chain rule to the first derivative. So what we're looking at here is we're going to have dy dx, which we know is dy dt over dx dt, which basically is y prime over x prime. And we want to find the second derivative. Now, the second derivative written in Leibniz's notation has the 2 between the d and the y and a 2 after the x in the denominator, indicating that it is the second derivative of y with respect to x both times. But what it actually means is the derivative of the first derivative. So the derivative d by dx of the first derivative dy dx. So what we do then is we split this outside derivative into the derivative with respect to t, d by dt, and the denominator dx becomes dx dt. So in other words, we add in this by dt into both parts. We make it complex, just as we did up here. We took the dy and made it dy by dt, and the dx and made it dx by dt. So we're doing the same thing to the outside derivative. And then we're taking the derivative of that with respect to dy dx. Now, the way that this works, because the dy dx is actually belonging in the numerator, this becomes the derivative with respect to t of dy dx divided by dx dt, provided, of course, that dx dt is not 0. If it's 0, it's undefined, right? And it won't tell us anything about concavity. So what does this really mean? To find the second derivative, find the first derivative, right? Using the formula we did before, dy dt divided by dx dt. Then take the derivative of that with respect to t and put that in the numerator. Then take dx dt and divide by it. And that will give you the second derivative, right? And of course, in graphical terms, what we're getting, of course, is information about concavity, whether it's concave up or concave down. So let's now look at example 5. This is one that we graphed before. This one was done in example 1. We've already found the derivative for x of t equal t squared minus 4t and y of t equal 3t squared or t cubed minus 6t, t between -2 and 3. We located the critical points, I believe we did. Let's go up there and let's see what we did. So that was example 1. Clicking on the right, we got that value right there. So I'm going to copy this off and we'll paste it down here. Right? I don't need to know about when t equals 0. right? So I have the formula here for dy dt. And then it says, next find the critical values on the curve, the t values and the ordered pairs. But I believe we also did that up here. So we have the critical points, which are here. Right, so we can paste that work down here. Again, remember, critical points come in basically whenever you have the first derivative equal to 0 or the first derivative doesn't exist, but the point does exist on the curve, right? So we have these right here. And then it asks to find both the t values and the ordered pairs, which we also did in example 1. But we did it right here on below the graph. All right, so let's paste this work down here. Let's leave a line there. All right, so we found these 3 ordered pairs, all right? So we have -3, -4, which turned out to be a relative minimum. 5, 4 turned out to be a relative maximum. So this was a relative min, this is a relative max, and this was neither one, neither a min nor a max, right? It was not a relative extrema. Okay, now we want to find the second derivative. Now this is new. This is something we haven't done yet. So remember up here, we found the first derivative. So let's copy off the first derivative, which is here, right? Because we need that first derivative in order to find the second derivative, all right? So we have the first derivative. And we're also going to need dx dt, which was 2t minus 4, but we can see the equation here, so we can do it again. Now, how do we find the second derivative? We take the derivative with respect to t of the first derivative, and then we divide by dx dt again. All right, so now we're going to apply that down here. So the second derivative of y with respect to x both times is going to give us the derivative with respect to t of dy dx. Always write the formula, and then by the end of the homework, you'll have it memorized without having to sit down and memorize it, because that's the pain. So this is going to be the derivative with respect to t of, and I'm going to multiply out the 3 times the t squared minus 1, just to make it easier to take the derivative. 3t squared minus 3 over t minus 2 over, now what is dx dt? Well, x is up here again, so dx dt would be 2t minus 4. Now I need to take the derivative of that numerator, which is a quotient, so you're going to have to do the quotient rule. Okay, so I've gone ahead and written out for you the second derivative by taking the derivative of the numerator using the quotient rule. So let's look at that now. So we have to take the derivative of dy dx, which is going to be the denominator t minus 2 times the derivative of the numerator, which is 6t, minus the numerator times the derivative of the denominator. And by that, we mean the denominator of the part we're taking the derivative of, which is t minus 2, all over the denominator squared, which is t minus 2 squared. This is still divided by the 2t minus 4, and I made it purely complex by writing the 2t minus 4 over a 1. So now the next thing that we want to do is we want to multiply out the numerator, and we want to get rid of the complex fraction. So the extremes are these right here. So the numerator becomes this part multiplied out times the 1 from the denominator of the denominator, which gives us this expression here. And it gives us the t minus 2 quantity squared times 2t minus 4 in the denominator. Now we can factor the 2 out there, and that's going to give us another t minus 2, which becomes 2 times t minus 2 quantity cubed. And then after we simplify the numerator, we get 3t squared minus 12t plus 3. You can factor out a 3. It's not going to cancel with the denominator, so I don't know that it's really necessary to do. It doesn't really simplify it a lot, but it may simplify if you have to plug in values for t. So let's go back. Now that we've done all this work, we've kind of forgotten what we were supposed to be finding. Okay, so it says calculate the second derivative and locate any critical points on its graph. Okay, we've done that pretty much. So we can see that we've got all the critical points evaluated. And now what we want to do is we want to look and see what it looks like on the graph. So here's our graph again, and we can use what we've done in order to determine concavity at a particular point. So what we found is the second derivative. So if we're looking at this, this is going to give us concavity at a particular point. So we know that we can find out where it's concave up and where it's concave down by looking at these particular values. And this gives us a formula which will tell us whether it's concave up or concave down at any particular point. So for example, up here, we use the value t equal 1, and it gave us that relative minimum at -3,4. So that was this point right here. It's clearly concave up there. We can plug in t equal to 1, and we can find that it is going to be a positive value, which means it's concave up. So again, we know that the second derivative at that point, if it's positive, it's concave up, negative, concave down. Okay, so let's now take a look at the next example, which is example number 6. In example 6, we have a parametric equation that we haven't worked with yet today. So we're looking at the formula for the second derivative of x equals t to the 5th minus 4t cubed and y equal t squared. And then we want to use this second derivative to determine if the graph is concave up or concave down when t equal 2. Now, obviously, we can also do by inspection, but remember that not all curves produce graphs that it's easy to tell by inspection. Sometimes the change is so subtle that the naked eye can't see it. And so this gives us an algebraic way of determining whether it's concave up or concave down. And then we want to know, of course, what point on the graph this corresponds to. In order to find the second derivative, remember we have to find the first derivative. The second derivative is the derivative of the first derivative divided by dx dt. So we need to find the first derivative. So this is going to give us dy dt over dx dt. So dy dt is here, y equal t squared. So the derivative of that with respect to t is 2t. And the derivative of x with respect to t is going to be 5t to the 4th minus 12t squared. All right, so we have that expression there. Could we do anything to simplify that? Well, I guess we could take out a t. Yeah, we could take out a t if we wanted to. We could factor out a t from the numerator and the denominator, and that would give us something slightly simpler. So this would give us 2 over 5t cubed minus 12t. Again, factoring out a single t. In fact, 2 would come out, but we only want to take 1 out because that's all that we have in the numerator. All right, so that t cancels that t. All right, and this gives us a simplified expression for dy dx. All right, now we want to go ahead and use this formula in order to find the second derivative. So I don't need nearly that much space there. So I can get rid of that space. So I'm going to apply my formula now. Okay, so I've written out for you the expression for the second derivative of y with respect to x both times. Remember, that means you take the derivative with respect to t of the first derivative, which is going to be the derivative of this formula that we found here. Now, a simpler way to take the derivative of this is to write it with a -1 exponent so that we can invoke the chain rule rather than having to do the quotient rule, which would be more difficult. So I wrote that here in this format, and then we're dividing, of course, by dx dt. Now, we'll be sure when you divide by dx dt that you don't use the reduced form. That's not dx dt. Dx dt is actually the 5t to the 4th minus 12t squared. You can always go directly back to the expression of x of t to find dx dt. So when I did that, I came up with the following. So this is my dx dt. When I took the derivative of this with respect to the chain rule, I got a negative to the front multiplied by the 2 that raised it to the -2 power. Then you have to take the derivative of the inside, which is 15t squared minus 12. and then all divided by dx dt. Now that got a little crowded over there, so I went ahead and simplified it and wrote it in complex fraction form. So I have a -2 times the 15t squared minus 12, derivative of the inside from the chain rule. And this came from the power rule. It had a -2 power, so I dropped it to the denominator. And all of this is divided by at dx dt. And I wrote the dx dt over 1 to make it purely complex. Now, the next thing I did was I went ahead and I separated it out a little bit. So I don't know if I can get this to go down a line or not. Oh, yay, I can. Okay, excellent. All right, so what I did here was I simplified it a little bit. And what I did was I took the denominator where I had 5t cubed minus 12t raised to the second power, and I factored the t out of the inside. Now they're both being raised to the second power, so that gives me a t squared times 5t squared minus 12 quantity squared. The second parentheses, I could factor out a common factor of t squared, which is here, and that leaves behind 5t squared minus 12. And then I took that t squared and moved it to the front, which you see here. Now that gives me 3 sets of 5t squared minus 12, which will give me 5t squared minus 12 cubed times t to the 4th in the denominator. And then I have -2 times 3. And the 3 came from factoring out 3 from 15t squared minus 12. It's tempting to want to say that cancels with one of the ones in the denominator, but this is a 15 and that's 5. They don't cancel, they're not the same. So don't make that mistake. Now, the next thing we can do, of course, is multiply out the -2 and the -3, and you get -6, 5t squared minus 4 divided by t to the 4th times 5t squared minus 12 quantity cubed. And this is our second derivative, all right? So we found the value of the second derivative. Let's now take that to determine the concavity at a particular point. So the next thing that we want to consider is what is the concavity when t is equal to 2? So here's our formula for the second derivative, and we want to evaluate this when t is equal to 2. So plugging that in, we can see that the second derivative of y with respect to x both times when t is equal to 2 is going to give us -6 times 5 times 2 squared minus 4 divided by 2 to the 4th power, which is definitely positive, times 5 times 2 squared, which is also positive, minus 12 quantity cubed. And again, what we're really looking for is the sign. If it's positive, it's concave up. If it's negative, it's concave down. And so that's really what we're looking for here. So we're going to evaluate this in here. This gives me 2 squared is 4, 4 times 5 is 20, 20 minus 4 is 16. So I have a -6 times 16 in the numerator. 2 to the 4th is also 16, so those 16s will cancel. And then inside this parentheses in the bottom, I have 2 squared, which is 4 times 5 is 20, 20 minus 12 is 8. And then I get this times 8 cubed. All right, so the 16s cancel, and I get -6 over 8 cubed. 8 cubed is definitely positive. I don't know what it is, but it's a lot. And then, is it 512? I'm not sure. Anyway, I'll let you guys figure that out. No, it can't be that big. Yeah, maybe it is that big. I don't know. Anyway, this is going to turn out to be negative. And because it's negative, that means it's going to be concave down at that point. All right, so we have some kind of graph that's concave down when t equals 2. Now we need to know what ordered pair that refers to. So we're going to come back up here, and we're going to copy off this equation again. So let's save before we copy that, because that tends to freak out the Word program a little bit when I copy off the math type. All right, and so we can see that that worked a little bit better by saving first. So we can paste that down here. So we have that equation right there. And we want to find out what ordered pair t equal 2 corresponds to. So when t equals 2, then we have x, which is going to be 2 to the 5th, which is 32, minus 4 times t cubed. Oh boy, I need to write this down. So I have 32 minus 4 times 8. Well, that's 0. Okay, so I get 0 for that one. And then 2 squared is going to be 4. So it's at the ordered pair 0, 4. And you can see this down here in the graph. I've produced the graph of it. We can come over here and look at this particular point. So let's go ahead and look at this on Desmos. All right, and I've gone ahead and moved this out to the point 0, 4. And you can see that A is at 2, so it's graphing. And it produces this graph that you see right here. Now, mine is going between -10 and 10, which I don't believe is correct. This is supposed to go, well, it doesn't say. Okay, so if it doesn't say, then we can assume for all values of t, and -10 to 10 is pretty good. So when we're looking at this one right here, if we're curious about what the orientation is, we can pull this back to the beginning and we can trace it, and it's going to trace one time. So it looks like, I can't see it yet. Whoa, all right, that kind of went way too fast. All right, so let's click on this and let's slow it down a little bit. Let's slow it down a lot, okay? And let's drag it back and let's play it again. So it's coming in there and then tracing there. Aha. Okay, so I think I see the path that it followed. It came in from the upper left. It traced this way, came through. And then went off in that direction like that. Now, another thing that you can do to find the orientation is you can take the slider bar and slide it back, and then you move the slider bar very slowly until you can see it appear on the graph, which is taking a while. There it is. So it's slow. There, it's right there, and then it comes to here, and then it slowly is going down around here. And then it's going up. Notice we have not reached t equal 2 yet. So the first time it hits 0, 4, that is not the place that we're talking about on the curve. We're talking about the second time it hits the 0, 4. And then it goes off from there. All right. So I hope this makes sense to you, what we're doing now and how we're using calculus with parametric equations. The next topic we want to consider is called arc length. And this is a way of measuring how long an arc is. So for example, if we're looking at this graph right here, I might say that I want to know how long it is. Let's change this up a little bit and make it go smaller. So instead of from -10 to 10, let's just go from -2, well, let's not make it -2. Let's make it -4 to 4. All right. So we can see a smaller graph. Now, we still can't see how far out it goes. Wow, I'm up to the 200s and it's still out there. So it must go way, 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 way out there. All right, and we could, of course, find the value when t equals -4 by plugging in -4 into this expression. That will give us the ordered pair. So that would be -4 to the 5th minus 4 times -4 cubed, all right? And we can figure out what it needs to be. And let's say that I wanted to know how long it is as I trace from these different values. And we might pull it in a little bit more and make it a little bit easier to find. Let's make it go from -2.5, if I can find my point, up to 2.5. And that should get me something that is on the graph a little bit more. Still way out there. So let's find how far out it goes. All right, so maybe out to 100 or something like that. And we can change the scale right here on X to go maybe from -120 to 120, and we can see that it's coming in like that. It's still further out there. This must go, oh, wow. All right, 10,000. So really, really far. All right, so when I'm looking at this one right here, I'm graphing this part of it right here. And let's suppose that we only want to know what that part is. I forgot to change this up here. So let's change this to negative 2.5 to 2.5. Okay, so if I'm looking at this region right here, and let's suppose that I want to square it up. Ooh, okay, maybe I don't want to square it up. Let's undo that. All right. So that's going maybe something like that. All right, so we've got this curve, and now we can see the whole curve, all right, from negative 2.5 to 2.5. And I want to know how long it is. In other words, if I take a rope and I put the rope along this curve, it's not a function, it is a curve. If I put the rope along the curve so that it matches the length of it, and then I straighten the rope out and I measure how long it is, how long is that curve? So that's the next thing that we want to study, and it's called arc length for a parametric curve, right? So when we're looking at arc length for a parametric curve, the idea is to take some smooth differentiable curve and divide it into subintervals. Now, this is a very typical calculus thing to do, to divide it into subintervals. And then we're going to approximate the arc length on the subinterval with the hypotenuse of a right triangle. The smaller we make the subintervals, the more accurate the approximation is going to be. We study this in more detail in section 2.4, but let's take a look at what we're doing right here. So we've got this blue curve here, which is a function. And what we're going to do is we're going to approximate this curving section of the blue graph right here with this straight line segment, which becomes the hypotenuse of a right triangle. So the right triangle, of course, is right here, and this becomes the hypotenuse of it. And so we're taking the hypotenuse of that right triangle and using that to approximate the length of the blue arcing curve over the subinterval between x sub 0 and x sub 1. So when you look at one particular region right here, you're basically taking this length that you've got right here and highlighted in yellow, and you're approximating it with the length of the hypotenuse. Now, obviously, this doesn't look very close, but as you shorten up the subinterval, they become closer and closer together, and you know what's coming next. As we take the limit, as that width goes to 0, they become equal to one another. Now, if we're looking at this equation right here, we can actually compute the length of the hypotenuse. So the hypotenuse, we'll call that lowercase l for length. So lowercase l, based on this right triangle that we see right here, and here's the right angle, has got to be the square root of delta x squared plus the square root of delta y sub I squared. So this is the width of the ith subinterval in both the x and the y directions. You square them, you add them together, and then you take the square root. It's just the Pythagorean theorem. So when we're looking at this, this gives us the length L of this part right here. So this is a lowercase l. So that's the length of the hypotenuse of the ith subinterval. Now we're going to assume that we're going to make a regular partition. Now remember, a regular partition, the lengths of all the subintervals are the same. It's not actually necessary. It's just necessary that the length of the widest one goes to 0 as we take the limit. But it does make the calculations easier if we make a regular partition. Because what we're going to do is we're going to multiply by a form of 1 of delta x divided by delta x, where delta x is the length of each subinterval because we made them all the same. So we take our formula for L, this is the length of the hypotenuse that you see right here, length of hypotenuse from the Pythagorean theorem, equal to the square root of delta x quantity squared plus delta y sub I quantity squared. Now, delta x is going to be the same for every subinterval because we made it regular, but delta y sub I will not be the same. It'll be different for each subinterval. So, for example, if we're looking up here at this graph, we can see that on this particular one, this becomes the y sub I here, and that's the y sub I there, and they're clearly different. They're not the same length, right? So they're going to be different on each one. But if you make the partition regular, all the delta x's will be the same. And so this right here becomes delta x, and this is the same width, which is also delta x, right? So once we have that, we can take this equation from the Pythagorean theorem and we can multiply by 1 in the form of delta x over delta x. Now we want to move the denominator into the square root, so we square it, and that gives us delta x in the numerator on the outside, and under the square root, 1 over delta x squared, because the square root of delta x is delta x, and we know delta x is strictly positive. Then I'm going to take this and I'm going to slide it underneath each one of those terms that were originally underneath the radical. And this is going to give me delta x squared over delta x squared, which is just 1. And this gives me delta y sub I, that length of the y change, squared divided by delta x squared. But they're both squared. So I can rewrite this as delta y sub I over delta x quantity squared. Now, you know that this delta y over delta x has to be a slope, and it is a slope, all right? It's the slope of the secant line there. Now, the function has to be both continuous and differentiable, and because of that, we can use the mean value theorem. Now, how are we going to use the mean value theorem? Again, a most valuable theorem. We're going to claim that there's some point c sub I in each subinterval such that the slope of the tangent line at c sub I, f prime of c sub I, is equal to the slope of the secant line. Oops, there's a typo in my notes here, so I have to go correct that. This should be the slope of the secant line. There we go, make that correct. Delta y sub I divided by delta x. So coming back up here to this graph that we see up here, basically what we're saying is somewhere in here, you can see the slope of this line right here, which is our delta y sub I over delta x, the slope of that line. And somewhere in here, there has to be at least one point, c sub I, where the slope of the tangent line at that point is equal to the slope of the secant line. That's basically what it says, right? That's the mean value theorem. So the derivative at that point equals the slope of the secant line. So then we're going to take that and we're going to replace in the formula this delta y sub I over delta x, where this is the slope of the secant line. And we're going to replace it with the slope of the tangent line at that particular point, c sub I. So now we have this equation right here becoming 1 plus the derivative at c sub I quantity squared. Now we're going to add up the lengths of all the subintervals to get the length of the entire curve or the entire arc. And we'll call that uppercase L for arc length. And this is going to be the sum of all the little lengths. So we have this square root here, f prime of c sub I quantity squared delta x. And we're going to take the sum of all of them. And then we take the limit as the number of partitions goes to infinity, which means the width of each partition is going to 0. It's the same idea. So you can either say the number of partitions goes to infinity, or you can say delta x goes to 0. Two halves of the same coin. So when we take the limit of a Riemann sum, we get a definite integral. So we have the integral from a to b. And again, what we're looking at here is this is a and this is b. So we're getting the integral from a to b of the square root of 1 plus the derivative of the function times the differential dx. Now, why does the f prime of c sub I become f prime of x? As these intervals get smaller and smaller and smaller and smaller, the value of c sub I starts to approach the value of the left endpoint, which is x. And so it just becomes f prime of x. So now we have our formula for the arc length, which we have right down here. It is the integral from a to b of the square root of 1 plus the first derivative quantity squared dx. Now, this can be calculated with respect to either x or y. And if we write it with respect to y, then we get the integral from y equals c to y equal d of the square root of 1 plus dx dy quantity squared dy, which sounds kind of weird. We don't actually use that one very often, but this is what we have, all right? And we'll study this again more in section 2.4. So this is the length of the arc going from the ordered pair a comma c on the graph to the point b comma d. So this goes from x equal a to x equal b, or y equals c to y equal d. Those are the same points, 2 points on the graph. All right, now we're going to manipulate this somewhat algebraically so that we can get something that looks a little bit better. All right, so when we manipulate this algebraically, we're going to take dx and we're going to rewrite it as dx equal dx by dt times dt. The dt's would cancel. This is a total abuse of notation. It's not what the derivative really means, but it works, so we do it. And then we have dy equal to dy dt times the differential dt. Why are we doing this? Why is this a problem? Well, because our functions are written in terms of t. So we want to get them written in terms of t. So to rewrite the previous equations, instead of having dy dx, which is f prime, quantity squared, we're going to write dy dt by dx dt quantity squared. And we're going to represent the dx differential as dx dt times dt. And this is going from x equal a to x equal b. And we have something similar over here on this one. We have dx by dt over dy by dt, because this is with respect to y, so it turns the derivative upside down. And we have dy by dt times dt. Now, we want to go ahead and rewrite the number 1 that you see there at the beginning of that radicand. And we want to write it so that we can get a common denominator. So we take this dy by dt over dx by dt, and we square the top and square the bottom. And so we rewrite this as dx by dt squared over itself, so we can get a common denominator. And I'm doing it on both of these that you see here. And once we have a common denominator, then we can write it like this. Now you may go, oh, I see what's coming. Because once they have a common denominator, this is a single term denominator and it's squared under a radical. Now, assuming that we trace the curve in the ordinary fashion from a lower x value to a higher x value, from a lower y value to a higher y value, then the square root of dx dt quantity squared will just be dx dt. Remember that when you take the square root of something squared, you should get absolute values. But if we trace in the normal fashion from left to right or from lower to upper, then it will turn out to be positive, all right? So once we have that, we take the square root of the denominators, we slide these out. You can see this is a dx dt in the denominator. You have a dx dt in the numerator. You know they're going to cancel, and that's going to give you something in terms of dt. All right, and over here we have a dy dt in the denominator, and we have a dy dt in the numerator. They're going to cancel, and that's going to give us something in terms of dt. Now we are assuming that it's traced from left to right and bottom to top, which means that those absolute values can be dropped and they cancel the other differential. And we're left with this formula here and this formula here, which amazingly are the same formula, right? This becomes the same thing here as you have here. The integrand is identical. What's not identical are the limits of integration. And the limits of integration are a bit of a problem because this goes from x equal a to x equal b, but the differential is now dt. And this one goes from y equal c to y equal d, but again, the differential is dt. So because the differential is dt, we would like to not have to revert back to x or y. So what we want to do is find out what t value corresponds to x equal a and x equal b y equals c, and y equal d. Now remember that these are referring basically to the same points. We're really going from the ordered pair a comma c to b comma d. All right, so those are the same ordered pairs. So what we do is we find the t value that corresponds to the point a comma c. We call that t1. And then we find the t value that corresponds to b comma d. We call that t2. And then we can change the limits of integration from t1 to t2. And then both of these formulas become exactly the same thing, because it will be the same t value for x equal a and y equal c. They're the same point, right? And that gives us one formula for the arc length of a parametric curve. So we take the derivative of x with respect to t and square it, plus the derivative of y with respect to t and square it, add them together, take the square root, integrate with respect to t, and the limits of integration go from t1 to t2 between those 2 points. All right, so here's the formal statement of the theorem. We have a plane curve, meaning in two-dimensional space. We have parametric equations x of t and y of t. T goes between at least t1 and t2, and we want to know what the length of that curve is. Assume that x of t and y of t are differentiable, because if they're not, we can't find the derivatives and we can't use the formula. So they need to be differentiable, and remember, if they're differentiable, they have to be continuous. Now, if there is a point where they're not continuous, like we saw in the last graph, there is a hard corner on this graph that you see right here down at the bottom. There's a hard corner there. What do we do about that? Well, we just make that be one of the places where we cut the integration. So we integrate from one place to another and from the next to the next, and that will make it still doable. All right, so let's take an example of one of these, and let's find the arc length for the parametric curve x equal e to the t cosine of t and y equal e to the t sine of t. This is a spiral curve, and I'll show you what it looks like. So it's right here, and it starts here and graphs around to here. The beginning part of it actually looks like half of the sideways heart, right? If you drew the other part mirror image, you would get a heart shape turned sideways. But that's not actually what the curve looks like. If we look at the actual curve and we allowed t to go further out to the side, we would see that it actually spirals for a long distance. Okay, so let's take a look at that one. All right, so it looks like this. Now, if I wanted it to go past pi, ours only goes to pi. But if I go past pi, let's say I go to 2 pi, you can see that it starts to spiral around. All right, you can see it's kind of coming around. There it is, and it's coming around like that. And if I made it go 3t or something, or 3 pi, it would spiral even more. All right, so it would start curving around there. So it creates this spiraling pattern that you see here. It gets wider and wider as we go out. But again, we only want the one that goes from 0 to pi. And of course, we're way out there in the 6,000s, so way, way, way out. And now we need to zoom back in so we can see what it looks like. All right. And drag and zoom. All right, so this is our curve that we have right here. If we want to trace it from 0 to pi, it goes along this curve right here. It's not moving terribly fast, and it goes to there. We want to know how long is that arc. All right, so we're trying to find how long the arc length is. So it begins here and it stops here. So now we're going to take our formula for arc length, and we're going to apply it to this formula that we see here. Now this one is actually a pretty nasty one. So I want you to go ahead and pause the video, work out the algebra and arithmetic, and then turn the video back on, and let's compare our formulas for the integrand before we integrate. The first thing to recognize is that both the functions for x of t and y of t involve multiplication, so you're going to have to use the product rule. So when you take the derivative of x with respect to t, you end up with e to the t cosine of t minus e to the t sine of t. Now, if you factor the e to the t out, it does make the calculation simpler later on. So it gives you e to the t cosine of t minus sine of t. We do the same process on dy dt, which gives us e to the t sine of t plus e to the t cosine of t, which gives us e to the t sine of t plus cosine of t. Our formula takes each of these derivatives, squares them, and then adds them together. So the next thing we want to do is we want to square them and add them together. So when we take dx dt, we take this e to the t and square it, and the cosine of t minus sine of t and square it, which basically means that we multiply it by itself. Now, if you multiply it by itself and you square the e to the t, you're going to get e to the 2t. And notice in here that you get this sine squared of t and a cosine squared of t, and they're both positive. Well, you know that sine squared plus cosine squared is 1, and that's where this plus 1 is coming from that you see right there. And then you do the same thing on the expression for dy dt, which is right here. So you square this part and multiply this part by itself, which is squaring it. And you end up with a similar pattern that you can see down here. So again, you end up with sine squared of t plus cosine squared of t, which gives you that 1. Now we have to add these together and put them under a radical, the square root. So we add them together as you see here. Notice that the e to the 2t is a common factor. So I can factor that common factor out. And that gives me 1 minus 2 cosine t sine t plus 1 plus 2 cosine t sine t. And that means that these 2 cosine t sine t's will cancel. And that leaves me with 1 plus 1 just gives me 2. So I have 2e to the 2t. So the integrand you should have gotten was the square root of 2 e to the 2t dt. Now I want to separate these two factors from each other. So this becomes the square root of 2, and the square root of e to the 2t, given that e to the 2t is always positive, is going to give me the following. So this gives me the integral from 0 to pi, which is the range over which we want to find the arc length. And this gives me the square root of 2 e to the t dt. Again, remember that e to the 2t raised to the 1/2 power just gives me e to the t again. All right, so then I'm going to integrate that particular one, which is super easy. It's just itself. And so I end up with the square root of 2 e to the t evaluated between 0 and pi, which turns out to be the square root of 2 times e to the pi minus e to the 0, which is 1, which is the square root of 2 times e to the pi minus 1, which turns out to be roughly about 31.31166, ... All right. So it's an irrational value. You've got e to the pi, which is definitely irrational, and the square root of 2 is also irrational. So definitely a nasty number, but it's about 31 units long, a little more than 31 units long. So when we look out here on the graph, what we're saying is if we put a rope along this arc length, we would need a rope that's about 31 1/3 units long, or feet or inches or whatever we're talking about. All right, and that gives us the arc length of that particular curve from 0 to pi. Now, if we want to evaluate it over a different interval, then we just change the limits of integration. It doesn't actually change the integrand. It just changes the limits of integration. Okay, so now we want to take a look at the next example, which is example number 7. And let me pull that one up higher so that it's not so far down. All right. So we want to find the arc length of the parametric equation x equal 3t squared, y equal 2t cubed. Now, this one turns out to have kind of a weird shape. It almost looks like a line, but it is not. It does have curvature to it. So when we look at this one, it's got right here, and there's this slight curvature that you can see to it right here, all right? So there is a slight bend in it. If you're not sure, you can always find the first derivative of it and the first derivative is not going to be a constant, which tells you, of course, that it does have some change in curvature. So now what we're looking at is we want to find the arc length over the interval from t from 1 to 3. And we can see that it is a pretty wide region. This is going from the ordered pair 3, 2 up to 27, 54. So we should expect that it should be relatively long. We could estimate it with the hypotenuse of a right triangle, which is what the arc length formula is all about. What we want to do, of course, is estimate it. So we're going to start by taking the formula, and I'm trying to see, no, I did not copy it down. So what we're going to do is we're going to take this graph and we're going to move it down out of our way. To right there. Okay, so that gives us plenty of room to work. So now we need to find dx dt and square it, dy dt and square it, then add them together, take the square root and integrate. So go ahead and pause the video, do the work, then turn the video back on and let's compare our work. So the first thing we do is find dx dt, which is 6t, and then we find dx dt squared, which would be 36t squared. Dy dt is 6t squared. Squaring that, we get 36t to the fourth. Notice that t is going between 1 and 3, so those will become the limits of integration. And then we're going to add these two values together and put them under the radical. And that will give us the arc length from t equal 1 to t equal 3. Now, when I got this over here, the next thing that I did was I had 36t squared plus 36t to the fourth. I had a common factor of 36t squared, which I factored out and gave me 1 plus t squared as the other factor. Now, because these are multiplied together under a radical, I can split the radical between the product. You can't split across addition or subtraction, but you can split across multiplication and division. So this gives me 36t squared under a radical times the radical 1 plus t squared. Now the square root of 36t squared gives me the absolute value of 6t multiplied by 1 plus t squared under a radical. But remember that our t value is going from 1 to 3, which means that t is strictly positive over the part that we're looking at for the arc length that we're looking at, which means we can drop the absolute values. So that gives me 6t times the radical 1 plus t squared dt from t equal 1 to t equal 3. This is a basic u substitution, which I've done down here at the bottom. You can see what I've got here. U is 1 plus t squared, du is 2t dt, t dt, which is this part, I didn't include the 2 or the 6, gives me du over 2, and then I change the limits of integration to u values. You could leave them as t values, but then you have to substitute back to t, and I didn't feel like doing that. So when I put this in here, I still have the 6, and then t dt becomes du over 2, which you see here. And then I replace 1 plus t squared with u, so I get the square root of u, which reduces to 3u to the 1/2 power du from u equal to 2 to u equal to 10. This is just basic power rule for integration. And when we apply the power rule, we get 3 times 2/3, which reduces to 2 u to the 3/2 evaluated between 2 and 10, which gives us this exact value that you see here, which is approximately 57.589. All right. So this is how we can find or estimate the length of an arc using calculus on parametric equations. I hope that you've enjoyed this and that you're ready and prepared to take a look at polar coordinate systems. When we go into polar coordinate systems, we're going to see the polar coordinate system is a type of parametric equation where we're measuring the distance from the pole, called the origin, and we're also measuring the radian angle from the positive x-axis, which is called the polar axis. So I hope you'll join me to learn about polar coordinates in our next video.